All right. Welcome back, everyone. Uh, Happy Friday, and sorry about what happened Wednesday. We'll just continue and pick up where we left off. I'll just recap what we had done, and then we'll move on. Just a reminder: the second midterm is next Thursday at 7 p.m., 7 to 9, online, and I'm requesting everyone to be online and please try, make sure your video cameras are on just so that everyone is here. And I know everyone is being ethical as they take the exam. So it'll be 2 hours, and you can upload your solutions after you're done, um, just like last time. Okay, so I'm going to continue if there's no questions or comments with chemical equilibrium today. And just to recap, we started with this notion of the extent of reaction. If we have some generic chemical reaction, as indicated at the bottom here, and the goal here is, since we can intuit that G is a function of epsilon at conditions of constant temperature and pressure, and we know that at a stable system, for a stable system, G is minimized, there must be some minimum in G as a function of the extent of reaction. And so once we can formulate G in terms of epsilon, we can take the derivative of G with respect to epsilon and see what that leads us to. And so what that entailed is developing equations for G in terms of epsilon. And I just want to, I always keep forgetting, but this is for ideal gases that we're talking about. And we're using ideal gases initially because we know that in general, G is equal to the summation of mu I n I. And we know that for ideal gases, for an ideal gas, this is just mu I at some temperature P naught plus RT natural log, the partial pressure of I over the reference pressure for that species, whatever we choose it to be. And often we'll choose it to be 1 bar. And so because we know what the chemical potential of an ideal gas is in a mixture of ideal gases, which I've just shown you at the bottom there, and we know that G is a function, summation of the product of mu I and I, we can use these two things in addition to the fact that dG d epsilon is equal to 0 when we reach this point. So at this point, we see that dG, which is a function of epsilon among other things, d epsilon is equal to 0. Okay. And so last class then, we started with this table. Okay, we said, all right, well, let's just pick some arbitrary epsilon. And we know that at that point, epsilon, we have some number of moles of A, B, C, and D, which are all ideal gases. And we label them n sub A of epsilon, and so on and so forth. And that epsilon in parentheses indicates that we're looking at the moles of that particular species at a particular value of epsilon, whatever that may be, whatever epsilon may be. Now we said that, all right, let epsilon change by a very small amount. And in this course, that means an infinitesimal amount, a differential amount, d epsilon. So now epsilon is our original epsilon plus d epsilon. Okay, so that's this guy here now. And so at that point, along this reaction coordinate, which is right here, epsilon plus d epsilon, which of course is going to be very close to the original epsilon point, which is in red, but I've just shown it exaggerated to make it clear to see. So now at that point where epsilon is equal to the original epsilon plus the d epsilon, the moles that we'll have of each species is going to be determined by the following expression. If we look at the one for A, is going to be the value, the number of moles of A at epsilon, which is just this guy right here. Okay, and then we add whatever was the change because epsilon changed by amount d epsilon. And so that change is just going to be the stoichiometric coefficient of A times d epsilon, right? Because that stoichiometric coefficient tells us how much the number of moles of A changes per amount of reaction that's going to take place. And we don't worry about sign, SIGN, at the moment, because we know from before that all of the stoichiometric coefficients have a sign associated with them. Products, positive, reactants, negative. Okay. And so once we have our moles at the 2 epsilons, we can just write G, which is a function of epsilon at constant temperature and pressure, in terms of those values of moles and the chemical potentials. And so for G at epsilon, we have this expression, which is just the summation of products of the moles of each species at epsilon times the chemical potential of that species. Okay, and then we look at G at the value of epsilon plus d epsilon. And at that point, we know that we have different moles, and the moles are now given by these guys, okay, right here. So it's just going to be, for instance, for A, it's going to be the chemical potential of A, mu sub A, times the moles of A at epsilon plus d epsilon. And you can carry that through for all the other species, okay? And of course, because epsilon is d epsilon is so small, we're going to assume that the chemical potentials remain constant during this interval of epsilon change, okay? So we don't have to worry about how the mu's change, okay? So now, in the case of G at epsilon plus d epsilon, we just substitute in all the moles, okay? And we know that all the moles are going to give us a term. If we look at this box, there's going to be terms that are just the moles of each species at epsilon times the chemical potential of that species. And then we're going to have a bunch of terms that are these products of the chemical potential times the stoichiometric coefficient of each species times d epsilon. And that's given here. So for A is the stoichiometric coefficient of A, mu sub A times mu sub A. And then d epsilon, since it's in every term, we can factor it out. Okay. So once we have these two expressions, so this guy and this guy, we can take the difference. We can say, what is the difference? So consider the difference. G at epsilon plus d epsilon minus G at epsilon. Of course, temperature, pressure, and moles are there, but we're not going to worry about them. They're implicitly taken into account. So this difference then, G of epsilon plus d epsilon minus G at epsilon, well, I'm not going to I think you can visualize the easy part, which is, if you look at the species A, in the G epsilon plus d epsilon equation, we have an NA epsilon times mu A, and that is the same as NA epsilon mu A in this guy. So these guys are all going to cancel. So all of the terms where we have the species moles at epsilon times the chemical potential of that species are going to vanish because they're in both places. Okay, just like for B, we have this guy here and we have this guy here. So when we subtract the two equations, those guys will cancel, and this guy will cancel with this guy, and this guy will cancel with this guy. Okay, so that difference, G of epsilon, d epsilon minus G at epsilon, is just going to be mu sub A times mu sub A plus mu sub B times mu sub B plus mu times that, plus the chemical potential of D times the stoichiometric coefficient times d epsilon. Okay. Any questions or comments? All right, pretty easy. But we know from our understanding of differential calculus that if we have G at epsilon plus d epsilon minus G at epsilon, and as d epsilon gets smaller and smaller and smaller in the limit that it goes to 0, this is just dg. Right? This is just that differential change in G, because we're taking the difference of G arising from a differential change in epsilon. So that differential change, so that change in G is really a differential change in G. So we have dG is equal to mu n mu A plus mu B mu B plus mu C mu C plus ud times the epsilon. Okay, now is everyone clear how I got to this expression? Okay. The only thing we had to incorporate here was this guy, this idea of dG. But that I think is straightforward. And so now we can take the d epsilon to the left, and what we have here is dG d epsilon is equal to mu sub A mu sub A plus okay. And that's pretty amazing that we have dG d epsilon as that summation. Okay. And we know now we know dG d epsilon is equal to 0 when we have equilibrium and we have stability in our system. So at equilibrium, okay. So we know that this sum of products is going to equal 0. Okay. So mu sub A plus this guy plus mu sub C plus mu sub D times mu sub D is equal to 0. And so this is the general expression for chemical equilibrium. So when you have a system, okay, when you have a chemical reaction or you have any particular system, and that reaction is an elementary reaction, you see that this is the criterion for chemical equilibrium. Okay. And it kind of turns out that the analysis, the spirit of the analysis that leads us to this is the same as the analysis we did when we were looking at the chemical potentials in a system and a subsystem, and we found that all of the chemical potentials have to be equal, right, at equilibrium. So this is an analogous result in the case of chemical equilibrium. Okay, so the other equilibrium we had was the equilibrium that arises from transport of mass or matter throughout a system. In this case, we have some transformation that's occurring where certain types of, we have atoms being rearranged into different forms. And so this is the criterion for chemical equilibrium. And now we can, now that we're here, we have basically all of the tools to determine something that you've seen before. The thing is, we have to now introduce our knowledge of each of the individual chemical potentials. Okay, and so we know that mu A, so again, recall, we are interested in temperature and pressure Tp. We are at constant pressure and temperature T. Okay, so mu sub A at a pressure of, and of course we have all of these other moles, is just mu sub A at temperature and some reference pressure. Okay, so we can, I'll tell you what that is in a moment, plus RT, natural log partial pressure of A in this mixture now, divided by the pressure of A at that reference pressure. Okay, and so I derived this result for the chemical potential of a species in a mixture, in an ideal gas mixture, a few lectures ago, and that was where we had this semi-permeable membrane in that discussion. And this is the form of that. So P sub A, this guy is the partial pressure of A now in this mixture at equilibrium. Remember, when we started our discussion of chemical equilibrium, we all agreed that at equilibrium, we're going to have all four components. In this case, we're only looking at A, B, C, D in our chemical transformation. So at equilibrium, we're going to have all four ideal gases present in the system. Hence, each one of those gases will have a partial pressure. And that partial pressure is denoted in the case of species A as P sub A. Okay, and P sub A superscript 0, which is in the denominator in that the argument of the log, P sub A superscript 0 is just the pressure of A in its pure state at temperature T and pressure PA 0 superscript 0. Okay. And this corresponds to the chemical potential of pure A at the conditions indicated in the parentheses. Okay. Now we can actually write this in a shorthand form as mu A with the superscript indicating that this is at this P sub 0 pressure, okay, and at the temperature of interest. So we'll just write that so we don't have to keep writing the P. And we'll just let this be the same. We're not going to change that. P sub A over PA 0. And that's the chemical potential of A at the conditions that we're interested in for this chemical reaction. Okay, and we can write the same for B, C, and D. Okay, so all you have to do is replace the subscript A with B, C, and D. And I'm not going to rewrite those because we already know that. So the interesting thing is now when we plug all of these expressions for the chemical potentials into this criterion for chemical equilibrium, you get something that is useful. Okay, so this is our chemical equilibrium criterion right here. Okay, and now we know what all of the chemical potentials are. Okay, and the nu sub A's are just stoichiometric coefficients. We can't really do much about them, so that's all there is there. So let's just plug it in. So I'll put the 0 on the left, okay, and that's equal to, what's mu sub A? Well, mu sub A is this thing I have in the last box, so I'm just going to write that. And that whole thing, that thing on the right-hand side of the equal sign in that box is going to be multiplied by mu sub A, which is the stoichiometric coefficient of A. Okay, because in this equation, we see that the chemical potential of A is multiplied by the stoichiometric coefficient. So what I'm going to do is take this equation and multiply it by the stoichiometric coefficient of A. We'll start with species A. And what that will do is give us a term that is mu sub A times, mu sub A, the stoichiometric coefficient of A, times mu A superscript 0. And it'll give us another term, which is the stoichiometric coefficient of A, nu sub A, times RT log of the ratio PA over PA superscript 0. It'll give us two terms. Each one is multiplied by the stoichiometric coefficient of A. Okay. If we think about it, we're going to get the same two terms for B, C, and D, those species. All right, so at the end of the day, we're going to have four terms of this form. We're going to have, in the case of A, right? So that's just the stoichiometric coefficient of A times the chemical potential of A superscript 0 at the temperature of interest. And we can write the same thing for B. So we're going to have this plus the same thing for C plus the same thing for D. Okay, so that's when you get, that's what you get, four terms for each one for each species when you multiply this term by the stoichiometric coefficient of each one of those species. Now we look at the RT log term for each species. Since we're going to have four species, we're going to multiply again by the stoichiometric coefficient. And so we're going to have four RT terms, RT log terms. Okay, so we'll have nu sub A times RT natural log PA over PA superscript 0 plus mu sub B RT PB over PB superscript 0 plus mu sub C RT natural log partial pressure of C plus RT natural log, oh, I forgot the stoichiometric coefficient of D, which would be here, plus RT natural log partial pressure of D over partial pressure of, or the pressure of D in that reference state, P sub D superscript 0. Okay. So now we're going to lump the first four terms in that last expression, 1, 2, 3, 4 together. Okay, we're going to lump those guys together, and we're going to call that something called delta G superscript. Okay, and that's going to equal mu sub A plus mu sub B plus mu sub C plus mu sub D. Okay, so we're just going to define that way. Okay, so there you have it. That's just by definition, so we don't have to keep writing all those four terms. So that's your reference state or standard state delta G of reaction. And what that is just that if you had on the left-hand side, on your reactant side, you had A and B not mixed, just A and B in their standard states or their reference state. That's why this chemical potential of each species has the superscript 0. It's some reference state for each species. And in that reference state, we're going to say that there's a chemical potential for that species. Okay. So this is just that summation of the stoichiometric coefficient times that chemical potential. Okay. And what we see here then is that since mu sub A is really this, it's an indication for a pure species of the partial molar Gibbs free energy. Remember, it's G over N. You can think of it that way. And if we multiply it by the stoichiometric coefficient, which sort of is an N, it tells us how many moles of A are involved per amount of reaction, per extent of reaction. Then we see here that we get the extensive delta G for this reaction. And this is analogous to delta H. This is analogous. Remember when we saw that we had this guy a few lectures ago when we were talking about thermochemistry? Well, this delta G reaction is the analog of that. So we take all of these guys, A, B, C, and D, in their standard or reference state, whatever that may be. We can choose what that is, multiply it by the stoichiometric coefficient, and we take the summation, keeping in mind that mu sub I is greater than 1 for a product, and mu sub I is, 0, and it's negative for a reactant. Okay. So in this case, mu sub A is less than 0, mu sub B is less than 0, mu sub C is greater than 0, and mu sub D is greater than 0. And so we see here that delta G naught of reaction is equal to nu sub A and nu sub B are negative. So now what we're going to write, and nu sub C and nu sub D are positive. So we can actually write this as the magnitude of nu sub C times mu sub C naught plus the magnitude of mu sub D times mu D naught minus the magnitude of that minus the magnitude of mu sub B times mu sub B at that. And so you see here that it becomes this difference. Delta G becomes the difference of products and reactants, okay, when we take the absolute value of their stoichiometric coefficients and we put in the signs ourselves, right? And so we see here that this is why this becomes delta G standard state for the reaction. Okay, so this is not delta G for this reaction. I want to keep recall delta G naught. Let me just. So we have our original chemical reaction here. Nu sub A plus nu sub B goes nu sub C plus nu sub D, right? This delta G of reaction is not the delta G of this, right? So we have here delta G of reaction at pressure and temperature. Okay, that's what this is. Okay. Delta G of reaction is not equal to delta G of this. And this you have to keep in mind. Okay. This delta G superscript 0 just turns out to be this combination of terms, which is stoichiometric coefficient times the chemical potential in this reference state for each species when we analyze our chemical equilibrium criterion, which is this guy. Okay. All right. So this was that intermediate step. Remember, this is our chemical equilibrium criterion. Okay. And the first four terms are now this delta G naught reaction. Now we're just going to take a look at the last four terms, the RT log terms. Everyone with me or no? Okay. So let me recap where we are now. So going back to our chemical equilibrium criterion, we have 0 is equal to delta G naught superscript 0 reaction. I combine those first four terms, and now I'm going to combine the RT log terms. Okay. So let's take a look at this. We have okay, so everyone has that. Okay, so let me just say this. We have for species A, we have mu sub A RT natural log PA over PA superscript 0. That's this term, the first term in the RT sequence, RT log sequence, right? But that's really just equal to RT natural log PA over PA superscript 0 raised to the nu sub A, the stoichiometric coefficient of A. Okay. We can do that because these are logs and we can take the exponent, right? We can do the same thing for B. And so what we'll get there is RT natural log partial pressure of B in this mixture at equilibrium times nu sub B, and so on and so forth for C. And D. Okay, so we'll have four terms, okay, and there are going to be RT log of something raised to the stoichiometric coefficient of whatever that is. And so all I'm going to do is say, all right, well, I'm going to take that and say, all right, take out the RT factor. And then what I'll have is RT times natural log of PA over PA to the nu A plus natural log PB over PB superscript 0 to the nu B plus natural log PC over PC to the nu C plus natural log PD. Okay, and so this guy, okay, is just an equivalent way of writing the last four terms here. This guy, this guy, this guy, and this guy. That summation, okay, can be rewritten equivalently as this guy. Okay, so now we can put everything together. So our 0, this chemical equilibrium criterion, is equal to delta G superscript 0 plus RT times all of these natural logs. So what can we say when we have a summation of natural logs?
Can combine them.
You can combine them. That's right. Sorry? Yeah, go ahead.
You make them products inside the argument.
Exactly. They become a product. So natural log of A plus natural log of B plus natural log of C, for instance, that just turns out to be natural log of A times B times C, right? Is that correct?
Yes.
Yes, right? Okay. So if you have a sum of natural logs, that just becomes the natural log of the product of whatever those things were. And so in this guy, I have a sum of natural logs. I'm just going to rewrite that as the natural log of a product And that product is just going to be a product of whatever was, you know, each one of those. And there you have it. Okay. Well, we're almost there. Now what we're going to do, we could go a few different ways, but I'm going to keep this very general. So I'm going to define something called K sub EQ, and that EQ is for equilibrium, and it's a function of T, a strong function of T. Okay, and I'm just going to define that as P sub A over PA superscript 0 mu sub A times PB over PB to the mu B PC over PC superscript 0C PD over PD superscript 0 times the mu D. And this K equilibrium of T is a general, for the ideal gas case, our equilibrium constant. Okay. And again, this is for ideal gas mixture. Okay. So I want you to write in your notes. I hope you're all taking notes and really put all these stars and ask, you know, somehow make sure you, when you review these notes, that you realize that this so far is for an ideal gas, right? The way we've written it, but you see how we've come across this equilibrium constant. So this guy is the equilibrium constant, and this is, you know, for all intents and purposes, as one must be careful when doing any kind of work, you know, this is what it is, and you cannot neglect any of the P superscript zeros, and you cannot neglect any of the stoichiometric coefficients or the partial pressures in this expression. This is what the equilibrium constant is for a mixture of ideal gases that are involved in a reversible chemical reaction. Okay, at constant temperature and pressure. Okay, and the temperature is indicated by T. Okay. Any questions? So this is something we just defined, but it comes out naturally from our criterion for chemical equilibrium. It just comes out naturally. So what we have so far then, if we go back to our chemical equilibrium criterion, 0 is equal to delta G superscript 0 of this reaction. That's that contribution from all of the species being in standard states and taking the difference of their standard state chemical potentials times the stoichiometric coefficients for each one, plus RT natural log K equilibrium of T. That's what this chemical equilibrium criterion comes down to. Okay, so where did this come from? And let me just finish it. So what we have here then is delta G naught superscript reaction at T is equal to minus RT natural log K equilibrium of T. And now, how many have people seen this last expression before? Delta G is equal to minus RT log Q log K.
Yeah.
Great. Which course? Was it a UD course?
Organic chemistry, Gen Chem with electrochemistry, the Nernst equation, it's everywhere.
Okay, good. Okay, so for right now, we've done it for ideal gas. You're right, it's everywhere. And so the particular thing that you have to keep in mind is that for the ideal gases, K equilibrium is this. Okay, so that's specific to ideal gases. So you can't apply this expression that I've shown you here for K equilibrium to anything. It can only be applied when you have mixtures of ideal gases, right? But again, don't memorize it. When you go back in your notes, think about how we got to this expression. If you do that, you will understand exactly when and where you can use this form of K equilibrium. This relationship between delta G reaction of T is equal to minus RT log K, that is very general. That's right. So in this case, I don't have any form. I haven't told you anything more deep about what delta G superscript reaction is. Okay, it's just some symbol, okay, but it represents something. And I have this minus RT log K equilibrium, which is a function of T on the other side of the equal sign. Again, it's just a symbol that represents something very deep, but it's just a symbol. But what's important conceptually is that they're related to this equal sign, okay? And that is general. So let me sort of take this out, because these two expressions that I've written here are very general, okay? It's only when you start putting in things for delta G naught and K equilibrium that things become specific and you have to be careful, okay? So, and these both arise from our chemical equilibrium criterion. Okay, they both arise from our chemical equilibrium criterion. Any questions? Was that clear what I just said? Okay, and that chemical equilibrium criterion now, remember, depended heavily, right? I mean, I could trace this back all the way to the first law, okay, but I'm not going to. It all goes back to the first law, actually first and second laws. So it all goes back to the first and second laws. This equation can be traced back all the way to the first and second laws of thermodynamics, believe it or not, if you had the patience to do it. But in the short-term past, the chemical equilibrium criterion comes about because we have dGt epsilon is equal to 0. And again, this came about from the combined first and second laws. Remember that inequality, we looked at that at constant temperature and pressure. And the fact that G is equal to sum of the mu I and I. Okay. Anything else? No. So that's it. This expression comes about because of this relationship. Okay. And in fact, this is a little bit more subtle, but we have to add in this is equal to mu I plus RT natural log of some things. Okay, this is a little bit more nuanced. Okay, but we saw that what's in here for an ideal gas is just the ratio of partial pressure to some reference pressure. Okay, so these three things, these two coming from first and second laws, you can trace them back, leads to these expressions that you may have been just given. Okay, so they all hinge on the first and second laws of thermodynamics. So whether you knew it or not, you were using the results of thermodynamics in the past. And yeah, Sheldon mentioned the Nernst equation. That's exactly right. You can formulate electrochemical cells and electrochemistry all in terms of thermodynamics and chemical potentials, right? And since we see here that K equilibrium is intimately connected to chemical potentials are at the heart of everything. Chemical potential, chemical potential, chemical potential. It's all about G and the chemical potential. Okay, so let me just, going back to this, any questions? This is a very important conceptual idea that I just discussed. Okay, so we know now that K equilibrium at T is this product, PA over PA naught, and PB over PB superscript, PC over PC, and then PD over PD. Okay, but we know that nu A, nu B are less than 0, and nu C and nu D are greater than 0. Okay. So what happens then is that we can write K equilibrium in terms of now for the ideal gas system as a couple of terms, and I'm going to let you figure this all out. Okay, we're going to have PC raised to the new C times PD raised to the new D divided by partial pressure of A times the partial pressure of B. Where now what I've done is put the stoichiometric coefficients in absolute value signs. And since nu A and nu B are negative, those partial pressures are going to be in the denominator of this ratio, and the partial pressures of C and D are going to be in the numerator. Okay, and here I've used the absolute values of the stoichiometric coefficients. And you've seen this before in your earlier courses when you looked at equilibrium constants, where reactants would be in the denominator of an equilibrium constant and products would be in the numerator. This is where that arises from. Okay, you were implicitly putting those plus and minus signs for the stoichiometric coefficients, but you didn't know that at the time. Well, perhaps you did. I don't know. Maybe they told you about it. But you see here now that this naturally arises. You don't have to think about it. It just happens that this is what it is. Okay, so that's that term with the partial pressures. And now we have another term that has all those P superscript zeros. Okay, and so that term is just going to be, let's see, we'll have PA superscript 0 raised to the nu sub A, PB superscript 0 raised to the nu sub B magnitude, and then PC superscript 0 C, PD superscript 0 D. And of course, they're flipped now because all of those superscript 0 things were on the bottom. Okay, and so the A and B, when you have that superscript 0, will go to the top in the second term, and vice versa for the C and D. And again, we're using absolute values for the stoichiometric coefficients. Okay, we're using absolute value for the stoichiometric coefficients. Any questions or comments? Okay. So this may be something that you've seen before. If all P sub I is equal to 1 bar, right? What happens is that second term is just 1, because everything is 1 bar, 1 bar, 1 bar. Okay. In fact, there's going to be some units on that bar, okay? But oftentimes we implicitly take that into account, and we're never told that, okay? And so I want to make the point here to connect to that when we look at this expression, okay? What are the dimensions, or what are the units of K? So if we look at this expression, this is the expression that we found, and this is from a purely theoretical, rigorous analysis of the chemical potentials for an ideal gas, and then of course the combination of first and second laws. Okay, so what do you think are the dimensions of K equilibrium?
Will it be however you define the molar coefficients? The stoichiometric coefficients.
But do they have units?
No.
Yeah, they don't, right? We can sort of give them some idea or notion of moles, but really they're not really, they don't have a unit.
Is it unitless?
Okay, why do you say it's unitless? I'm not saying yes or no. I just want to know your rationale. That's all. Can you give me a rationale or a reason? Take a crack at it.
In the equation, it's, I guess, the partial pressures over partial pressures. So the units would cancel.
Very good. Very good. Okay, excellent. So that's exactly right, Khalil. So in this expression, we see here that K equilibrium is a product of a ratio of pressures. So if PA, let's say our partial pressure of A is a half bar in the system at equilibrium, and PA superscript 0 is 1 bar, we have a half a bar divided by 1 bar, that thing is unitless. The same goes for all of the other terms. And so we have something that's unitless being raised to some power, which again has no units. Okay? So this whole thing is unitless. K equilibrium has no units. Okay, that is a fundamental fact. K equilibrium cannot have a unit. That's a great answer, Khalil. The other way someone could have answered is that question is, well, we have delta G naught of reaction at T is equal to minus RT natural log K equilibrium of T. You can't take the natural log of something with units. Okay, so this is, you're taking the natural log of K equilibrium. You cannot take the log of something with units. Okay, that's not allowed. Mathematicians do not allow it. Okay, so whatever you're taking the natural log of has to have no units. So K equilibrium is unitless. And so from our expression, delta G reaction at T is equal to minus RT natural log K equilibrium of T. What are the units of delta G, or what are the units of G? They're going to, what nature are those units? Like, are they speed? Are they velocity? What units are they?
Joules per mole, or energy per mole.
Energy, right. G, well, in this case, G is extensive, so it can't be per mole. Right? If I were talking about molar, then I would have had this, or a sub m. So delta G has energy units, and on the right hand side, what's going to give us the energy units? It has to be RT, right? Because R is blah 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 per Kelvin, so it's energy per unit Kelvin, I think.
Yeah, joules per Kelvin.
Joules per Kelvin, and so we multiply it by T, and we're going to get
Joules or energy.
right. And so the two sides have to be equal in terms of their dimensions, and so this guy then can't give you any units. Okay, so that's another way to sort of justify that. So take-home message here is that K is dimensionless. And so I know some of you are thinking, well, when we had some reactions, you'd get K equilibrium as like A, B over C, right? Do you remember those kinds of equilibrium constants? Some of you might. Ostensibly, this seems to have any dimension, doesn't it? So we're going to figure out why, that even in this form, there were some tricks that you weren't told that make this dimensionless. And in though you were given equilibrium constants in terms of dimensions rigorously, they can't really have any dimensions thermodynamically. And I demonstrated that to you right here through all of this analysis of the ideal gas mixture. So any questions? So everyone now, so to go back, right, that's what we did here. We found this point. We found this point, and we found that at that point, this holds. Okay, that's what happens at that point right here. Okay, that's what we've shown. Any questions? Okay, and that was an application of all of that theoretical toolbox, the stuff in that toolbox that we've learned, first and second laws, and then all of those criteria. this is a practical thing now that comes out of all that stuff. Okay, this is how we use it, and that's what it's good for. It allows us to come upon these things. Okay, I think I will stop there and just ask once more if there are any questions that people want to ask. Okay, then I will end the meeting and I will wish you all a good weekend. Be safe and take care.